Hi, welcome to Distinti's gyroscope model. This is channel trailer number 17. This will be released to my Patreon folks before it is released to the general population. Hold on, let me get my pen set up here. Just make sure the pen works. Okay. I will show you secrets about gyroscopes that no one has ever seen before. Mainly because the legacy models that have been published in books for over 200 years are gibberish. And Rule of Acquisition 3.2 says the greatest obstacle to scientific progress is the delusion that we think we know what we're doing. And you gibberish, you say. That's going to be your first reaction. And you're going to say, well, what about all the gyroscopes for navigation and all the guidance systems for missiles? How would they work if we don't know how gyroscopes work? Well, I have the fourth rule, or the third rule of acquisition, which is monkey do does not mean monkey know, which let me give you a little insight. I'll give it Exhibit A, fire, which is also known as combustion. Our lack of knowing what fire was did not stop the Bronze Age, did not stop the Iron Age, did not stop firearms development, did not stop the steam or the Industrial Revolution. We used fire for 100,000 years to effectively cook, heat our homes, boil water, clear land, sanitize wounds, cauterize wounds, cremate dead bodies, brand animals, forge tools, smelt alloys. We've got steam engines working. We still didn't know what fire was. And we're really good at using fire for war. In fact, gunpowder was developed long before we knew how combustion worked. So we don't necessarily have to know how something works to put it to good use. Okay, and we didn't even know the coherent understanding of combustion did not come about until the last half of the 19th century, or about 150 years ago. That's from Encyclopedia Britannica. So don't get the false notion that just because we can put something to great use means we actually understand it. That is complete and utter nonsense. But the interesting thing is those damned engineers have developed alternate modeling methods that are sufficient to mimic gyroscope behavior. Okay, in other words, they came up with this thing called finite element modeling, which is a beautiful, wonderful thing you can put into a computer. And just by doing simple linear modeling, those simple, and I'll show you with the derivation I came up with that gyroscopes can be easily modeled with simple linear finite element modeling. But unfortunately, because they were able to mimic the behavior, they just assumed, well, it must be in keeping with these 300-year-old equations. And those 300-year-old equations are junk. But you say, well, why don't we use the finite element models? Well, yeah, we could, but they don't really give us insight onto what's really going on. They're going to give us a right mimicking behavior of a gyroscope, but they're not going to allow us to see anything you couldn't see by just looking at a gyroscope by itself. I mean, if you can mimic the behavior of something, that doesn't mean you really understand the behavior. And what I'm going to show you with the Distinti models of the gyroscope, I'm going to show you things about gyroscopes that you're not going to be readily apparent from the finite element modeling or just by looking at a gyroscope yourself. Now, if you go to Wiki, the gyroscope is a device used for measuring blah, 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 and according to the conservation of angular momentum. That is what the legacy models are based on, the conservation of angular momentum. And if you've seen my previous video, Rule of Acquisition 26, conservation of angular momentum is violation of the accounting tell. And it means that, doesn't mean necessarily it's wrong. I'm going to show you these are wrong, but it just means there might be a more fundamental version. Okay, now what I'm going to do is I'm going to demonstrate some interesting gyroscope behaviors by looking, and we're going to show some clips from Professor Eric Laithwaite's demonstrations. In the low bar, I'm going to put the link so you can go look at it yourself. It's like an hour long. He does a lot of other very interesting demonstrations. Note 1, the video quality is rather poor. And I ask you to watch how the precessing gyroscope drooped down over time. In other words, when it's spinning, every time it spins around in its precession, it's just a little bit lower than the time it was before. That's very important. That's extremely important to understanding why it works, and we'll demonstrate that when we get to our models. And just be careful, he makes a lot of claims I have problems with about, oh, it's totally inertialess and all this other stuff. But, you know, I really want you to look at the demonstrations. Don't really listen to what he has to say. Okay, here's one of his
You can see a
demonstrations.
little mutation taking
And
place.
one thing to look at is
I
slowly
can do the
drooping down.
trick I did with the two whirls. I can make it rise
and he
up by
spins it up
pushing
and it
it a
goes
little
up.
faster.
But over time,
Notice
it's
the
slowly going to
precessional
droop
speed
down.
now is very large because the torque is very
See,
large
it's
because the
drooping
gyro
down.
is offset a long way. Now,
That droop is
suppose
very
I'd
important.
clamped that
That's
there
not explained.
and tried to rotate it at that same speed. Watch what happens.
Well, that's disingenuous. but
Why
we
did
won't
it
cover
topple?
that later.
If I bring out the gyro to that position, it is free to topple over. I shall need, in fact, a little weight to hold it down. Of course, in any other position, it's all right. It's only when the offset mass comes out there that it weighs over like that. Now, we'll spin this up, and then I'll take the weight off and ask Mr. Coates to catch the gyro as it falls. Now, if you'll come round
Watch,
there
this one
and
droops
ready to
too.
catch it
See
when I
how
lift
as
the
it's
weight.
moving, it slowly droops down?
Next time round, it's coming off.
Every rotation, it's slow, a little bit lower than it was before. That's
He
very
cheated
important.
again, says the man in the gallery. Did he really? Yes, he pushed the aluminium back a bit. All right, he'll pull it forward a bit. More than a bit. Pull it forward a lot. The whole of the tower is now well outside the end of the bench. That is about 1 revolution per second. I'm going to stick a peg in a hole.
See, when
And
it
it did
stops
not
its
break
precession, it
off the
falls
peg.
like a rock.
Because
This
then
is
we've
one of the
made
best
one
experiments.
in which the rim has been subdivided into a lot of little masses on spring wires, so that when I set it in motion, turn it to the camera, you can see this. If I now waggle it side to side, the inner ring that is, you can see the precession taking place not about the point you thought, not about the midpoint here, but about the top and bottom. And if I give the inner ring a spin, you can see this
Look how it
leaning over
tilts.
like a dinner plate. Can you see that?
Now watch what he does.
Incidentally, I said
It
that
slows
when you had
down.
the gyro going, it wanted to maintain its axis of spin. Why isn't that stopping the minute I let go? It wasn't what the other gyros
It did stop when he let go. He had to
There's
spin
one
it
point
back
to
up.
think
Did you
about.
see
I'll answer
that?
that next time. Thank you.
Did you see that? Play that back. He says, why doesn't it stop when I let go? But he pushed it to keep it
There
going.
is much experimenting to be done. I've only...
Okay. Back from Eric Laithwaite's, what we're going to do first is we're going to show how the legacy physics explains this. So here we have a gyroscope, and right now for starting conditions, it's got a bearing on one side that's being supported. Right now it's just being supported while we're spinning it up. And what we're going to do is we're going to apply a spin, and these arrows over here help you see, because it's kind of hard to see which direction this arrow goes, but it's spinning in this direction. We're going to spin it up. Okay, and we're going to call this the spin axis, which is going to be along X for starting purposes. This is the Y-axis and the Z-axis. We're going to explain what these mean in a moment. Okay, once the support is removed, gravity is going to pull down on this guy, which is going to give it a torque, which is going to want to spin the wheel this way, or want to make it topple to the right. And we're going to show that coupling axis by this wheel over here, this desire to turn the gyroscope along the y-axis in this direction. Okay, so what does regular physics say? Well, regular physics says, well, angular momentum is going to be conserved because the nature is now trying to rotate the gyroscope in this direction. The energy from this spinning wheel is going to cause the wheel to turn in this direction, so that these arrows oppose these arrows. Let me show you that in the next. Okay, I just did that. Okay, and so that's basically what they're saying is happening, is that this is going to rotate so that these arrows will go in the opposite direction as these arrows. In other words, what you infer from this is the rotational kinetic energy of this wheel is going to counter the force of gravity. And that's got to remember that. They're inferring that the rotational kinetic energy of the wheel is going to oppose the torque caused by gravity. Okay? Remember that. That's going to be an important point going further. So again, it's implied that the rotational energy of the disk is consumed to cancel the coupling torque by gravity. Okay, but how does this energy couple through the low friction bearing? Let me do a little demonstration what I mean. Okay, so here's the demonstration. Here's your run-of-the-mill gyroscope, and we're going to use the same dimensions that we have in the diagrams. Here's our pedestal, and what we're going to do is we're going to put this here. Now, we're not going to spin it up because I really can't get this thing up with the little piece of string they give you to enough force or enough velocity so it can actually run perpendicular like this. So we're just going to use this as a demonstration to show the point I'm trying to make. So what's going to happen is, because gravity wants to rotate it this way, and if we spin the disk in this direction, which is this way, well, the way that it's going to roll to compensate for the force is this way, so that see how my fingers now are going in opposite directions. But here's the problem. What they're saying then is that this rotational energy must couple along this axis to keep it from falling over. But here's the fundamental problem. Okay? I can't couple energy from the wheel to the frame. So how do we keep the frame from falling off if I cannot couple energy along that axis? Except maybe for a little bit of bearing friction, there is no way in heck that energy from the wheel could couple in such a way to keep this thing from falling over. So that cannot possibly be the mechanism by which this thing works. And why this has been in textbooks for like hundreds of years just blows my mind. Okay, that explanation in the textbooks is complete gibberish, because there is no way that you're going to couple energy from the rotating element to along this axis here. No way. Except for a little bit of bearing friction. So there's no way this energy could be used to keep the thing from falling over. And I'm going to show you that in my derivation. Thank you. Now, coming back from that, why doesn't the disk spin down faster? It doesn't look like that the spinning disk is under any kind of degrading. It looks like it's just spinning down slowly from friction. It doesn't look like that when you release the disk that all of a sudden now there is a burden on it and causing it to spin down faster. Now the other question, which is important, is if the disk acquires more rotational momentum from precession than from gravity. In other words, the gravity aspect here, okay, trying to rotate it this way doesn't really cause much rotational velocity there. We get more rotational velocity from the precession of the wheel. So if we're getting more angular momentum from the precession than we are from gravity, shouldn't there be another action of this wheel that's going to counter that? Which way would the wheel go to do? The wheel would then have to go up. And then once it starts to go up to counter that, now we got rotational energy that's actually going in this direction. And so so now we have these competing forces. We have basically a runaway feedback system where one thing's going to cause another, that's going to cause another, that's going to cause another, and each thing after that is going to have more rotational velocity than the thing before it, according to the progression of what I'm showing you. And that's what I'm trying to say here. That was my little demo. And so the legacy models violate so many of the rules of acquisition. I'm not going to read these to you. My Patreon folks should be familiar with some of these. Okay, so let's derive the new model. We're just going to consider in this derivation a tiny little speck piece of the model, a little piece of the wheel, a little point mass part of the wheel. And we're going to do it by point mass. Okay, so the velocity of the wheel, of this little point mass, v, is equal to the rotational velocity. W omega here is the rotational velocity of the wheel. Excuse me. R is the vector distance from the center of the wheel to where the point mass is. And therefore, the velocity of the wheel, the vector velocity, is found by omega cross R. So that's the velocity of a particle on the wheel. And any particle in the wheel can be modeled by that equation. So let's say let's looking down from the top now, and we see this little particle of mass m is rotating along the top of the wheel. And let's say at that moment, we actually try to spin the wheel in this direction. Well, as that particle is crossing the top of the wheel, it's now going to be deflected in another direction. And because we're deflecting this point, there's going to be an equal and opposite reactionary force in this direction. And my friends, that's the entire explanation of everything that goes on in a gyroscope right there. It's nothing more than we're deflecting the particles along the axis of rotation. Now, it actually happens all along the wheel, but at the edge, far edge, the effect is zero, and it gets more and more intense as you get to the top of the wheel where it's being spun. So continuing the derivation, so that particle at the top of the wheel was initially going in this direction, and then because we applied a little bit of displacement, it was now going in this direction. And the amount of displacement can be the angular velocity times the delta t. And so if we put these two velocities here together, okay, and this little arrow here is the delta v is equal to the acceleration times delta t. And that is approximately equal to the angular velocity times delta t times velocity. And if we divide both sides by delta t, that gives us delta v over delta t is equal to, and then we take the limit as delta t goes to, that should go to 0. That's a mistake. As it goes to 0, typo, then we're going to get that acceleration is equal to the angular velocity times the velocity. Okay, so if we put the velocity equation and the acceleration together, then we have acceleration is equal to, we're substituting this into here, is equal to this because we're going to vectorize it. And then we know that force equals mass times acceleration. So vector force is just going to be a vector acceleration times mass. And that is the equation for any given particle on the wheel of a gyroscope. Now all you have to do is integrate this over all the particles in the wheel, and you can come up with a great finite element model of how it works. And this, my friends, is so simple that existing finite element models don't even have to do this. They could just do their normal finite element modeling, and they're going to get this answer. And I'm going to show you in a Veritasium example that they in fact do. Okay, now one thing that's interesting about all this, because these are all signs, cross products are signs, it means that the force, here's the axis of rotation here, the force is majority is up here, and when you get toward the side of the wheel, it goes to 0. And so if you were to look along the side of this wheel, these force arrows would make a nice linear ramp up one side, and that's consistent with what we see with the Laithwaite, where his wheel is basically just a straight line when he starts rotating it. You saw that in the previous demonstration. So this explains that. I don't know how they explain that with their, conservation of rotational energy. That doesn't make any sense to me how they could possibly explain this. And this is how precession really works. It's really a negative canceling feedback system, or a negative feedback system. Step 1, once the pillar is pulled out, this spinning wheel is going to start falling. It's actually going to move. And it's going to start moving fast enough. Okay, along this axis, we're going to get this rotation, which is going to cause these forces here. These forces are going to start it into precession. Once it starts rotating along this axis due to precession, that's going to cause these forces at the top and bottom of the wheel, which are going to cancel gravity. It's that simple. Okay, if there were no friction or air viscosity in the system, this system would defy gravity forever. Now I ask a question, should it? because none of the energy in the wheel, okay, these arrows are perpendicular to the velocity of the wheel. So they are not going to retard the energy in the wheel. So none of the energy in the wheel is going to be used countering gravity, which is amazing. And we're going to cover that a little bit more later. So getting back to it, the fall, let me go back up and do this again. The fall is going to start rotation along the green axis, which is going to cause the forces here. These forces are going to cause the wheel to precess along this blue axis here. Okay, this blue motion is going to cause the blue forces, which are going to oppose the torque due to gravity. And again, if there were no friction, this would just continue on forever and ever and ever. But because there is friction, there is frictional force. Okay, this precession is going to lose velocity because of the friction in the bearings, and because as this thing rotates through the air, it's going to impinge the air. And therefore, it's going to fall back from the optimal speed that's necessary to oppose gravity. What that's going to do is cause it to droop down just a very little bit, which is going to keep just a little bit of force going to oppose this friction. And so what you're going to truly see, and this is something you can't pick up by the finite models, or you would probably not notice it in the experiment, but you'll notice in the demonstrations I show, every rotation of the systems that were shown are lower than the preceding ones. That's because of the bearing friction. And this thing constantly needs to droop down to keep these little forces going so that they oppose the friction, and therefore preventing this thing from just falling off. Now, if you block the precession, this thing falls like a rock, like it should. And Laithwaite does demonstrate that. And that's as simple as it is. Now, I was going to make a little signals and systems system block diagram to show how all these things intercouple. But I figure this is a good exercise for people that are taking signals and systems now. This will take me about 2 hours, and I really don't have the time this weekend to get into this. In other words, it'd be a kind of a system where your gravity goes in, and this goes out to a block that converts the torque to a rotational velocity in one dimension, and then this rotational velocity gets coupled into another dimension, which then couples a torque that counters the gravity, and it would be like a simple feedback system from signals and systems. Okay, it'd take me 2 hours to get through all the details of that. I just can't waste the time on it right now. But again, the most amazing thing is that it does not appear that any of the energy of the spinning wheel is consumed in opposing the gravity. Now, I know physicists get all bent out of shape when I use the term consumed. In other words, what I'm saying is none of the rotational energy is dissipated opposing gravity, dissipated in other forms of energy. Now, that kind of makes sense because gravity is supposedly a conservative field, and conservative fields cannot add energy or subtract energy from a closed system, which a spinning wheel is. So, maybe I did everything right. I mean, I don't know. I mean, I'm trying to overcome my damage from all my college training. Did I make a mistake? Did I oversimplify? I'm going to leave this question to others because I have more important work to do. And why did I get off on this gyroscope thing? Well, my Patreon subscribers are aware of the PDX3 generator. Now, this video is going to be released to the Patreon for a week before it's then released to everybody else. So, just keep that in mind. Okay, and the paradox 3 generates voltage from rotating magnets which cannot yet be accounted for. It's not over unity. It's just components of magnetism that cannot be explained yet. In trying to explain the results, I started looking to other poorly explained systems that violate the rules of acquisition, and the gyroscope has been on my radar for a long time, and this gave me a reason to go look into it to see if there was anything special there that could help us explain the rotational things that we're seeing with the paradox 3. But since there's nothing here that will help with the paradox 3, I am leaving this for others to continue. It's just not that important. Once you realize how mundane it is, as it should be, that there's really nothing here that's going to help us out on the Patreon side. So I'm leaving it in all your other hands. You can deal with it. You can take it to its next logical conclusion. That's fine by me. Just give me credit for getting you started at least. And by the way, for those folks that are out, the Paradox 3 was going to be released to everybody once I figure it all out, but it's going to be released to my Patreon folks for at least a week, if not a month, before it's going to be released to everybody else. Okay, and by the way, once I derived the simple model for the gyroscope, it was very apparent that the simple finite element modeling used in software and all this other stuff would have no problem modeling the behavior by default, including modeling the very strange behaviors of what's known as the alternate axis theorem. And it's funny because if you observe this video, and I'm going to put the link for this video, we'll look at little clips of it in a moment, is the Veritasium guy. He goes and explains, all this can be explained by conservation of energy, and then he tries to get a mathematician to help him. The mathematician won't answer his, whatever. So instead of trying to go through the explanation of how it works, he ends up going into a computer model, and the computer model gives him the right answer. Of course it should. This is the comedy. But they assume then that because the computer's model is right, he assumes that because the computer model is right, that all that gibberish he talked about with the 300-year-old models must be correct too. And that is not the case. This is what I've been saying, is people don't realize that sometimes, engineers go off on a different track and don't realize that what they're doing has no bearing on old physical models that physicists hold to. Okay, and I'm going to show you some Veritasium clips right now.
What you are looking at is known as the Janabekov effect, or the tennis racket theorem, or the intermediate axis theorem, but we'll get to that. Now, you may have seen clips like this one before, but in this video, I will provide the best intuitive explanation of how this effect works. A number of simulations and animations have been made. But if you really want to understand what's happening, most people resort to the math, including
simulations
me
work.
In the past.
Watch them try to explain the math.
The mathematics is kind of complicated, and boy, is there a lot of math. But the explanation is not mine. It actually comes from one of the greatest living mathematicians, Terry Tao. He has won the Fields Medal amongst a host of other awards. And for this video, I actually asked him for an interview, but he declined because he's busy solving centuries-old math problems. So, fair enough. But that's okay, because we have the explanation he posted to Math Overflow in 2011, and it goes like this. Imagine we have a thin, rigid, massless disk centered in our coordinate system. Now add some heavy point masses to opposite edges of the disk on the x-axis. Even though they're point masses, I'll put some large cubes around them.
Okay, I forgot to put a concluding slide on this video set, but I think it's complete. You get the idea that it's such a simple model. It makes very much sense. It follows the behavior of the gyroscopes. It's very consistent with what finite element modeling does. And again, because it's so mundane, it's not worth me looking into anymore. I got more important things to do. Anyway, thank you. And thank you to all my Patreon folks for being patient during this